this summary video on nuclear and particle physics. Okay, the first thing I'm going to look at is the basics of atomic structure. It's nucleon number and proton number. If you look at this atom, let's look at carbon-12. So carbon-12, our nucleon number is going to be 12. That's the total number of nucleons, which is protons and neutrons inside the nucleus. And proton number is exactly that. It's the number of protons inside the nucleus, or we can call that the atomic number. Okay, so a large angle alpha particle scattering experiment. So essentially what they did was they fired loads of positive charge alpha particles towards a thin layer of gold foil. Okay, so most of the alpha particles went straight through, meaning that most of the atom was empty space. Okay, a few of them were deflected, meaning that there was positive charge, which causes the repulsion. Finally, only a small fraction of the alpha particles were deflected straight back to large angles of deflection, meaning that there was this large concentration of positive charge in the middle. Positive charge concentrated in the center, which we now know as a nucleus. Okay, so this experiment was fundamental in changing how we knew atomic structure. Before the nuclear model, there was a plum pudding model, which had a ball of positive charge with electrons embedded inside it. There's large mass positive charge spread equally and electrons embedded. Okay, but however, this couldn't explain why most the alpha particles went straight through, because again, the mass was equally spread out. This led to the nuclear model developing. So you've got the nucleus in the middle. It's concentrated positive charge, and most of the atom was empty space. That's why most alpha particles could just go straight through. So the key differences that we have in this model are most the atom is empty space, it's positively charged center, which is nucleus, positive center, and most of the mass is concentrated in the center. In the center. Later on, we developed this. Chadwick, who would discover the neutrons, and eventually Bohr would discover energy levels and electron shells. Okay, so the process of thermionic emission is when a metal is heated. Is your metal, apply heat to it, and the electrons which are inside the metal, see, as there's a sea of delocalized electrons, positive ions, the electrons, as they're heated up, they gain enough kinetic energy to break free from the surface, meaning that they can flow as an electric current. You can think about it as the metal is being heated, the electrons are kind of boiling off the surface, meaning that they're free to move as an electric current. So essentially, when the electrons have enough thermal energy to exceed the work function, that's why it's called the minimum energy needed for thermionic emission, work function represented by phi, then electrons have enough kinetic energy, so high enough velocity to escape the lattice and essentially boil off the surface and move as an electric current. Okay, so electric magnetic fields in particle accelerators and detectors. So essentially the key sort of rule of thumb is that electric field acts in the direction of motion, so force acts on the particle. Cool. sort of parallel, and work is going to be done. So work is done, so the particles gain energy, kinetic energy, greater velocity. So it's electric fields that actually accelerate the particles. Magnetic fields, however, so the force acts perpendicular to motion. So work won't be done because the force isn't in the direction of motion. So work not done. However, since the force acts perpendicular to the motion, there's going to be a centripetal force acting towards center, which means that the path of the particle is curved. It moves almost as circular motion of the particle is curved. Good. Okay, so a LINAC is a type of particle accelerator. It literally just means linear accelerator. And exactly as you can assume, it's self-tubes in a line. Okay, let me just draw that bit. We'll see that the length of the tubes increases as we go along. We'll see why that happens. So as we set the electron side, there'll be an electric field with alternating potential difference. So this electric field is also alternating. So electric field applies a force. The electron experiences a force inside electric field. Experiences a force. Work is done. And it has more energy. More kinetic energy, so higher velocity. Essentially, it's the electric field that accelerates the electron. A key point that we need to know is that the polarity of adjacent tubes is always going to be opposite. So we've got electron going here. We want to accelerate it towards this. So we're going to make this plus. This one's going to be negative. This one's going to be positive. So as the electron's going through, let's imagine it comes out here. So then we want the polarity of this next tube to flip. We want it to accelerate towards that and be repelled from this. So it goes towards this side. So we're going to change the polarity. That's why we've got alternating potential difference. This one becomes negative. This one becomes positive. Goes through here. So we've said that the polarity of the adjacent tubes is opposite. Opposite. And what that means is actual acceleration occurs in the gaps between the tubes, not in the actual tubes themselves. Occurs in gaps. Okay, lastly, we need to know that the frequency of the alternating PD or electric field remains constant. And that's constant. But that means the time taken in each tube must be the same to avoid getting out of sync. That means the tubes need to get longer as you go along. Tubes get longer as velocity increases. And it's just speed equals distance over time. Since time is constant, speed increases. Distance needs to increase as well. Increases. So length of tubes increases. A cyclotron, on the other hand, is different, but essentially is the same thing. Start with the alternating potential difference or electric field. Force acts on protons this time. Work is done. More kinetic energy. So velocity increases. Good. However, the key difference here is that now we've got magnetic field. Magnetic field. So the proton experiences a force. Proton experiences force which is perpendicular to its motion. Is per to motion. So that causes a centripetal force acting towards the center. So the proton has circular motion, or rather the path of the proton is curved. It's curved. Now the process is roughly the same. So we'll say that the proton is accelerated in gaps between D's. D's as in these things, because they look like D's, so they're called D's. Last thing, just like before, the frequency of the alternating PD is the same, so time spent in each D is constant. That means as velocity increases, V increases, radius of path increases as well. We'll see why in just a moment. Okay, in terms of particle detectors, it's roughly quite similar as well. Particle detectors. The best example for this is a mass spectrometer. Okay, so a mass spectrometer, generally, what it does, it can detect particles of different masses. So it's good in identifying relative abundances of isotopes. Okay, so this is our mass spectrometer. You've got an electric field here and our magnetic field here. Okay, so firstly, our samples are ionized using electron gun. So electrons are knocked off. So they all have a positive charge, generally 1 plus. And now you've got all these positive particles in our electric. Okay, so in the electric field, the particles are accelerated. Though they all have the same velocity. So they're accelerated through the electric field. Once they reach a magnetic field, the magnetic field just curves their path. Sort of deflects it. So this is useful as larger samples or more mass is deflected less. So it's going to end up at a different point at our detector. So if you imagine this one has a larger mass, it's not going to be deflected as much. It has a larger radius. This one is deflected by quite a lot. Just imagine like this, deflected quite a lot. And that leads to our mass spectrum forming. So our x-axis can be mass of charge. Now you've got copper 63 and copper 65. So a larger mass is going to end up here, smaller mass is going to end up here, and that's how you can find our relative abundances. Okay, so we mentioned before that as velocity increases, the radius of the path is going to increase as well. Now we're going to learn why increases. Okay, so you have F equals mv squared over r. That's our centripetal force. Our force in the magnetic field is BQV. just set those equals. mv squared over r equals bqv. You cancel out one of the v's, so you have mv over r equals bq. mv over bq equals r. So I've got this to prove that velocity, as velocity increases, radius is also going to increase. But what is mass times velocity if not just momentum? Momentum. So we can prove that r is equal to momentum over bq. And this proof is really important looking at particle tracks, conservation of charge, energy, and momentum. And that's where we can apply this. Look at this, particle short half-life decay into muons. So we need to analyze this particle track. To explain what conclusions can be made about the particles. Okay, first thing we can see is that the radius of the pion is decreasing. Pion's path is decreasing. So you can conclude that momentum is decreasing. So velocity decreases. We can also compare the radii of the positron and the antimuon. So positron has a much smaller radius. If you imagine antimuon, since it's looking kind of like a straight line, has a really large radius. It's going to move something like this. So it's have a huge radius. So positron, lower radius, or smaller radius rather. Slower momentum than the antimuon. We can also learn the charge of the positron. If you look at the direction of the particle pion and the positron, the same paths, same direction. So they must have the same charge. So positron charge equals pion charge. They also proved that using Fleming's left-hand rule. And now we can look at the antimuon. You can see that the track sort of stops here. So since it has such a short track, is a really small lifetime. It doesn't exist for very long. Lastly, we can consider all of our products. We've done antimuon, neutrino, electron, neutrino. That's what we need to look at now. So there's no path that we can see for electron neutrino. And that's really useful for us because we can say that it must be neutral. Those neutral particles never have tracks because the whole point is that it relies on ionization of particles. Neutral particles can't really ionize anything, so it won't have a track. No track. Cool. Okay, so this quite a small part of the spec, but it's a really complicated one as it relies on wave-particle duality. Duality, which means that particles such as electrons exhibit both particle and wave characteristics. For example, electrons have a wavelength. Electron wavelength, and that's what's being used to investigate structure. So the de Broglie wavelength is lambda equals h over p. So this is Planck's constant. And it's just momentum, mass times velocity. So if we know that lambda equals h over mv, then for high energy, so it needs to be a high velocity. Velocity, so high kinetic energy, to have a wavelength. So that's small enough that it can be compared to proton size. To proton size or proton diameter. So that's the whole point. It needs to have a high enough velocity That means they have high enough energy so that the wavelength is small enough that it's similar to the size of a proton. I can investigate the size of nucleons, so proton or neutron, as they're relatively similar sizes. Okay, so in particle physics, we'll learn that everything is made up of fundamental particles known as quarks. So we've got baryons, like neutrons and protons, they're made of 3 quarks. So neutron, okay, mesons, on the other hand, made of 1 quark or 1 antiquark. So it's never 2 quarks. That's an important distinction. It's quark and antiquark. Got leptons, fundamental particles, and you've got photons, which is a force carrying particle. So it carries electromagnetism. The other force carrying particles are gluons, carry the strong nuclear force. W and Z bosons, which carry the weak nuclear force. Okay, collectively, these fundamental particles are called bosons, as opposed to fermions, which are leptons, you've got here, and quark. Okay, so there are 3 generations of quarks made of 2 quarks each. So there are 6 quarks total. 1, 2, 3. Our first generation is our up quark and our down quarks. Up quark has a charge of 2/3 plus 2/3 of electron charge. Down has minus 1/3 electron charge. So most of matter is made of these 2 quarks. We've got proton, which has structure of UUD. That's 2/3, 2/3 minus 1/3. It goes positive E. That's our proton charge, positive. And neutrons are UDD. You have 2/3 minus 1/3 minus 1/3. So it's a charge of 0, so it's neutral. Next, we've got charm and strange. Again, plus 2/3 E minus 1/3 E. Last, we've got top and bottom, plus 2/3 E, plus 1/3 E. Okay, so the reason we had to predict the top quark instead of just finding it naturally is because it doesn't really exist for that long because of its extreme mass. It rapidly decays into a W boson and a bottom quark. So we had to rely on our knowledge of the symmetry of the charges to learn that the charge is going to be the same as up and charm. So it's plus 2/3 for electron charge. Likewise, there are 3 generations of leptons, so 6 leptons total. So yeah, 1, 2, 3. So you have your electrons, your electron neutrinos, so Greek letter nu for neutrino, muons, muon neutrino, and tau particle, tau neutrino. So these go in increasing mass. So mass. All of the charges of these leptons are minus 1e, so same as electron charge, and charge of the neutrinos are 0, as we've seen before. Okay, so you need to know that every particle has its own antiparticle. Best example is electron and positron. So these same mass, different charge. And if they ever interact with each other, they're going to annihilate each other and release massive amounts of energy. Annihilate, release energy. Okay, next we need to learn how to determine if particle interaction, the equation, something like this, is possible using charge conservation, baryon number, lepton number. Strangely, there's one that they're missing, I think. Strange conservation. Conservation. Okay. So charge is self-explanatory. So baryon number, exactly what it says. baryons have +1, anti has -1, everything else just 0. Lepton number is the same, lepton +1, anti -1, everything else is 0. Strangeness is a bit different. Strangeness, so if you have a strange quark, it'll have a -1. But anti-strange, it's going to have a +1. Okay, so now we've got Einstein's famous equation, E equals mc squared. But what does this actually mean? So imagine you've got this particle moving at incredible speeds, really large speed, to have a large amount of energy. If you were to use kinetic energy equals half mv squared, you might get v being greater than the speed of light, which just isn't possible, right? So the whole point of this saying introduces mass energy equivalent. And this is what forms the basis of special relativity. Essentially, at really high speeds, excess energy is converted to mass. So if you have excess energy converting to mass, then you won't have the excess energy leading to something like this, where our estimated velocity is greater than the speed of light. So kinetic energy not enough such that V is greater than C. Good. A little bit of conversions. So mega electron volts and giga electron volts. So electron volts is a unit of energy, and that works because, well, it equals QV, charge times potential difference. And that's how you can find really small amounts of energy. As electron charge is 1.6 10 power minus 19 coulombs. And mega electron volts over C squared, and that's mass, and that just uses this formula right here. Okay, last bit of the spec brings back more special relativity, and this is the concept of time dilation. Essentially, time experienced is different based on your speed. So essentially, the faster you move to space, you move, slower you experience time. So if you have a particle moving at a massive velocity, moving at high velocity, it's going to experience time slower. Experiences time slower. So it has a longer life, if that makes sense. So the factor which dictates how much this changes is called the Lorentz factor. This isn't needed, but it's still worth knowing. So it's 1 over root 1 minus v squared over c squared, where v is the velocity of our particle. So as v approaches c, v, so as it approaches c, then this is going to approach 0, right? So this factor rapidly increases. So as our particle approaches the speed of light, approaches speed of light, and then experience time much slower, so has much longer lifetime. Cool. It's something a little bit easier now. So let's write a particle equation for this collision. So a proton collides with a proton, produces proton, neutron, and a pion. So a proton plus proton produces proton plus neutron plus pion. So let's look for conservations. So baryon numbers conserved, 2, 2. Charge is not conserved yet. Go +2 on this side, +1, 0. But this needs to be +1. We've got pi plus as our product. And lepton number is irrelevant. There's no leptons involved. Next, give the quark structure. So he said proton is UUD. 2/3 plus 2/3 minus 1/3 gives us +1. Neutron is UDD, gives 0. And our pi plus is made of a quark and an antiquark to give us our +1 charge. So it can be U anti-D. So antiparticles are represented with this bar on top. Right. Next, convert mass of this to kg. So we have 140 times 10 to the 6 mega electron volts times electron charge, 1.6 and 10 to the power minus 19 over c squared. 3 times 10 to the 8 all squared, which gives me 2.49 times 10 to minus 28 kg. Okay, last one. Conservation of momentum and energy in producing the pion. Okay, so we know that the mass is going to be 140 mega electron volts. Mass of pion, 140 mega electron volts over c squared. So the energy, the rest energy, will be 140 mega electron volts. So the extra mass after the collision, or rather the extra energy, is converted to the mass of pion. So of E equals mc squared. Then this would make sense because energy would be conserved, right? Energy conserved. As our energy is 140 mega electron volts, and our change in mass is exactly that, it's 140 volts, so c squared times c squared. So that checks out. So energy is conserved. However, if we look at our conservation of momentum, for momentum to be conserved, all 3 particles after collision must have momentum, right? So that means all of them need to have velocity. Must have v as mass times velocity. So if they all have velocity, then they all must have kinetic energy. So there needs to be more energy to facilitate both mass of pion and kinetic energy of pions, such that momentum is conserved. Therefore, what's the question want? Suggestion is correct. Therefore, more than 140 mega electron volts. More than 140 is needed. Therefore, the conclusion, the suggestion is incorrect. Perfect. Thank you. Hope that helped.